So this first one here says a student takes a 12-question multiple choice quiz, but they did not study, and they need to randomly guess each answer. Each question has 3 possible choices for the answer. Find the probability that a student guesses more than 75% of the questions correctly. Just set up the probability distribution function. You don't actually have to do the calculation. Okay, so what I have said here with this problem doesn't require you to use the binomial distribution table she gave you. And it doesn't even require you to know how to do the factorial stuff that I've already talked about. Here's the thing. The table that she gave you wouldn't work for this question. It almost works for this question. She gave you a table, and the table off to the side says n equals, and then she's got 10 on there, 11 on there, 12 on there, and then it skips down to 15. So the only things that she could ask you to do if she were to give you a binomial distribution and she wanted you to use this table, your n would have to be 10, 11, 12, or 15. But there's also another part, because here, this is a 12-question multiple choice quiz. So I almost was like, oh, cool, this question that I wrote will work with her table, except it won't. And here's why. If you look across the top of this table, it's really, really tiny. It's got the p values, and that's the probability of a success. For this question, we had 12 multiple choice, but each of them had 3 possible answers. So the probability of success, if you're guessing, is 1/3, or the p would be 0.333333 forever, but 0.33 would what we would be looking for. If you look on this table, the p values, she's got a 0.3 and she's got a 0.35. We don't have a 0.33. So we can't actually answer this question using the table, but I have one from her previous practice midterm that we can use this table for. So we will go back and use the table. I'll show you how to use the table, but we don't want to use the table on this one because it won't help us. That's okay. It's going to let us set up the probability distribution function, which I think is the more important skill. Okay. So out of 12 questions means your n for this is 12. Because each question has 3 possible answer choices and we're guessing here, the probability of a success, if I put it as a decimal, is 0.33. If I want to make it exact, the probability of a success is 1 out of 3, if you're guessing, right? So then my q, which is the probability of a failure, what would that have to be? 2/3. It's always 1 minus the probability of a success. So if I do 1 minus the probability of a success, that's 1 minus 1/3, which will give you 2/3. So indeed, my q is 2/3. Okay. Another part that we have to pay attention to is it says, find the probability that a student guesses more than 75% of the questions correctly. We don't put percentages into our probability function when we're trying to figure out like the binomials. We choose a number. So we would say, what's the probability that we got more than 10 correct? Or what's the probability we got less than 2 correct? So I need to know how many questions is 75% of 12. Do you know how to do that? 75% of 12? It's 9. How'd you do that? You're correct, but how'd you do it? You multiply 12 times 0.75. If you have a calculator, then you're probably not freaking out about that. If you are freaking out about that, another way we could say 75% is 3 out of 4. Do you agree that's still 75%? 3 divided by 4, if you put that into your calculator, is 0.75, so it'd be the same thing. If I take 3/4 and I multiply it by 12, and I'm just going to go ahead and put 12 over 1 so you keep track of where numerators and denominators go, then this is going to be 36 in the top and 4 in the bottom. And 36 divided by 4 is 9, so that's another way that we could get that 9. So you're absolutely right. 9 is the number of questions we're asking. So when they're saying, find the probability that the student guesses more than 75% of the questions correctly. What they're really saying is find the probability that X is greater than 9 in this problem. If we're letting the random variable X be the number of questions they're answering correctly, we want to know the probability that we get more than 9 of them correct. Probability of getting more than 9 correct means we could get 10 correct, or we could get 11 correct, or we could get 12 correct. So this is the same thing as finding the probability that X is exactly equal to 10 plus the probability that X is equal to 11 plus the probability that X is equal to 12. So we got to find all three of those things. And fortunately, it doesn't actually need us to do the calculation. It just wants us to set up what that would look like. So for the probability that X is equal to 10, we put 12 choose 10 times the probability of a success we said was 1/3. And we always raise that to the power of the bottom number there. So that's going to be to the 10th power. And then times the probability of a failure we said was 2/3. And we raise that to the power of 12 minus 10. And that would give us, if we went through and we did that, that would give us the probability that X was equal to 10. So probability that X is equal to 11 is going to be 12 choose 11 times the probability of a success raised to the power of that bottom number 11 times the probability of a failure raised to the power of 12 minus 11. So if we did that calculation, that would be the probability that X was equal to 11. So we got one more. Probability X is equal to 12 is going to be 12 choose 12 times the probability of a success raised to the power of that bottom number 12 times the probability of a failure raised to the power of 12 minus 12. And this says we don't actually have to do the calculation part, but if we did, we'd be doing that calculation separately. We'd do 12 factorial divided by 10 factorial times 12 minus 10 in parentheses factorial. We figure out that number, and then we use the calculator to help us get that part. And we do the same thing for this one and the same thing for this one. We'd multiply it all out. But if it says just set up the probability density function, we're perfect. We leave it like that. Okay. In terms of you using the table, we can't on this one because our probability of a success 1/3 isn't one of the choices on her table, but I'll show you one in a few minutes where we can use the table.
Laying it out factorial, it's 12 factorial divided by 10 factorial times 12 factorial times 10 factorial.
So here, if I wanted to do this calculation, it's always the top number factorial divided by the bottom number factorial, and then in parentheses, top number minus bottom number. And you put the factorial on the outside of the parentheses. Okay. So this one would be 12 factorial over 11 factorial times 12 minus 11 with the factorial on the outside. And this one would be 12 factorial over 12 factorial times 12 minus 12 with the factorial on the outside. That would be 0 factorial, and 0 factorial is always 1 by definition. And so you could do this one without the table if they actually wanted you to solve it. You'd go through and do that calculation, and then whatever number you'd get, you'd multiply it times 1/3 to the 10th power, and then you'd multiply that by 2/3 to the 2nd power. Then you'd do this calculation, you'd multiply it by 1/3 to the 11th power times 2/3 to the 1st power. And then this one, when you do it, if it's 12 choose 12, I know it's going to come out to be 1. It always comes out to be 1 if the numbers are the same. times 1/3 to the 12th power times 2/3 to the 0th power, which would also be 1. But this one said you don't actually have to do the calculation. So you didn't have to do that part. Okay. Suppose that the duration of a particular type of criminal trial is known to be normally distributed with a mean of 21 days and a standard deviation of 7 days. Okay. So they gave us two pieces of information here. They said that you have a mu of 21, and they said you have a sigma of 7. First question says, in words, define the random variable x. What could we say that the random variable x represents in this case? Yeah, the duration of this particular type of criminal trial. And I'm going to write in days because that's the unit that they're using in the problem. Perfect. Part B says, if one of the trials is randomly chosen, find the probability that it lasted at least 24 days. Okay, it said one of the trials. So when it says one of the trials, we're just using our normal Z formula. If it said, if a sample of 30 trials were selected, then we'd be using our central limit theorem, and you'd be dividing that standard deviation by the square root of the duration, right? So in this case, what we've got is not a central limit theorem problem because it just says 1, or we already talked about how you could have used that square root of the n formula, but square root of 1 is just 1, so it's not going to change the calculation part. So what we're doing is we're using that Z formula. Z is equal to the X that they give you minus the mean divided by the standard deviation to get ourselves a standardized score that's going to let us then go use that Z table for us to find out a probability that it lasts more than, or it says at least, not more than 24 days. At least 24 days means 24 days or 25 days or 26 days or more. Okay. So for us, the X value you're plugging in is the 24. The mean was the 21. And our standard deviation is 7. So we have 3/7. But to use our table, I need to turn that into a decimal. So 3 divided by 7 gives us, if I round it, 0.43. And I'm rounding it to 2 decimal places because the table only goes out to 2 decimal places. So this is positive. So I need my positive Z-score table. And I'm looking for the probability for this one that's going to come from the table. When I get that probability, am I going to keep that as my answer, or do I need to do 1 minus that? And how do I know? Yeah, this one's going to be a 1 minus. How did you know that? At least. Because it's an at least, we got to do 1 minus the probability once we go figure out what the probability is. So in the end, we're going to do 1 minus the probability for our answer. But I'm going to go find the probability first. So 0.43 on my Z table 0.4, and then I'm coming over to the 3. I got 0.6664. Okay, so if this question had said, find the probability that it lasted less than 24 days, you would have kept that number. That would have been your answer. But because it says at least 24 days, we got to do 1 minus what we just got. And we get 0.3336. And so we normally answer this as a percentage. So I'd say there is a 33.36% probability the trial lasted at least 24 days. Questions on that one? The next one's going to require us to be careful. It's related to that question. It says, consider the criminal trial situation described in problem 4, and suppose we randomly sample 9 trials. Now I feel like we're in a central limit theorem type problem. Find the probability that the total length of all 9 trials is at least 225 days long. Okay. So it's tempting to think we're just jumping in and we're going to divide our standard deviation by the square root of 9. You might first go, we can't do that because central limit theorem says we need to have an n that's bigger than 30. But what part of the question in the original wording of the question makes me go, that's actually not what I'm worried about? Central limit theorem is normally when n is 30 or greater, but our n in the problem that they're asking us, they're giving us a 9. So I'd be like, ooh. But what's telling me that that's okay? Normally distributed. Yeah, this key phrase right here, normally distributed, tells me I'm not worried about that. When we're worried about it is when we don't know if the distribution is normally distributed or not. If it's a different size, like if it's n is not greater than 30, we normally can't go use the central limit theorem, but we can if we already know that it's coming from a normal distribution. We're okay then, not a problem. But that's actually not what we're going to go do in this problem. Question?
No.
No.
Oh, in the homework, one of the problems had said if we needed to know whether or not the distribution was formally distributed, but we were given a sample size that was greater than 30. So it's like that's what you're
If it's greater than 30, I don't care what kind of distribution we got. The central limit theorem is so cool that it says if you've got a big enough sample size, we don't actually care if the distribution is normally distributed. But in this case, they only gave us a sample size of 9. So I actually care for this one. I need it to be normally distributed or I can't go use central limit theorem. But the central limit theorem thing I need to use for this one is a little bit tricky. And it's on the formula sheet. And a lot of students were like, I don't know what this formula is down here, Jen. It looks hecka scary. Let me show you the formula that we're using. The bottom of the formula sheet, the one we're using, is the one down here that has the sum signs on it. And how do I know that? Okay, here's how I know it. There's a key word in here that says Find the probability that the total length of all 9 trials. When they're saying a total in there, I'm thinking we're adding some stuff up. So there's a sum happening here. Okay, so let's take a look at what this formula actually says, because it looks hecka scary, but it's not actually that bad when we break it down a little bit. Okay, so that formula at the bottom of her formula sheet says that the sum of x, the sum of the random variable x, is approximately normally distributed with the mean of the sum. So when she's got that little sum sign with the x there, it's actually like, it didn't like type the way I would like it to. This should be like below. It should be the mean there with this down below as a way of saying we're talking about the mean of the sum of the x's. The way we're going to calculate that is we're just going to take the n, which is 9, and we're going to multiply it by the mean that they gave us in problem 4. So they told us the mean of all the trials was 21 days. So they're saying, well, what if there were 9 trials? Well, if there were 9 trials and each trial has a mean of 21 days, we would just take 9 times that mean. So they're saying, take the n, that's 9, and multiply it by the mean that they gave us, 21. 9 times 21, it makes sense if you think about like, oh, well, if the mean of one trial, mean length of one trial is 21 days, but they're saying, hey, do it for 9 of them. We just do 9 times 21. That's all that formula says. This says if we want the standard deviation for the sum, what we're going to do is take the square root of the sample size. So the sample size is 9, so we're going to do square root of 9, 3. And we're going to multiply it by the standard deviation that they gave us, which I think was 7 days. So it'll be 3 times 7 days. I might just be making those numbers up, but we'll try. Yes.
Just for clarification, for the CLT theorem for normal, not the sum, is the keyword mean. That what the keyword is?
Like average.
Or average, yeah.
Like, how would you know it's the top formula instead of the bottom formula?
Yeah.
So it would be, yeah, that you're finding the mean for the sample. And so when she puts that X there with the bar over it, that's saying the mean of the sample. But when she wants the mean of the sum, the keyword you're probably looking for, if it's a word problem, is the total. There's probably a total in there somewhere. She might say sum. That would be more clear, but they don't always say sum. This one says total. Okay, so we had from the previous problem that the mean was, we said the mean was 21 and the standard deviation was 7. So I'm going to write that down. The mean is 21. The standard deviation was 7. That's from problem 4. But now we want the mean of the sum. And that's supposed to be n times the mean that we just had from the original problem. So our n in this problem is 9. So I'm going to do 9 times the 21. And that gives us 189. So they're saying that the average length of 9 trials should be 189 days. The average length of 1 trial is supposed to be 21 days. The average length of 9 trials should be 9 times that. So 9 times 21 is 189. Okay. They're saying that the standard deviation of days for 1 trial should be 7. And we got a formula saying that the standard deviation for the sum is equal to the square root of n times the standard deviation of just the 1 trial. So square root of n is going to be square root of 9. And the standard deviation for 1 trial was 7. So this is going to be 3 times 7. Or 21 days. So this is the information that we're going to use for this problem. We had to use the information they gave us from the last problem to do it, but we're going to use that the mean is 189 and the standard deviation is 21. We're going to still use the Z formula. This time, the X that you're going to use in your Z formula is going to be that 225. And when we're going to subtract the mean, we're going to subtract the mean of the sum. And we're going to divide by the standard deviation of the sum. So they said, find the probability that the total length of all 9 trials is at least 225 days long. So we're going to put 225 minus the 189 divided by the 21. And I got 1.71 if I round it. That's a Z. We're going to use our Z table to go get a P. Once I get that P, am I going to keep it or do I have to do 1 minus it? 1 minus it because it says at least. So we're going to do 1 minus the P for our answer. Yeah. So P is something, and then we need 1 minus the P for our answer. Okay, so I'm going to go look up 1.71 on my positive Z-score table. So 1.71 is 0.9564. 9564. Cool. So if this had said, find the probability that the total length of all 9 trials is less than 225 days long, then you'd keep that number. But because it says at least, we got to do 1 minus that number. All right, so I got 0.0436, and we would normally write that as a percentage. So I'm going to say that there's a 4.36% chance, or there is a 4.36% probability that the total length of all 9 trials is at least 225 days. So not particularly likely. All right, that was the end of my practice midterm. This is an old one of her practice midterm. Okay. The first question on there is a problem she's already given you, or it's at least a problem we've already looked at together. Maybe I gave it to you, I don't remember, but we've seen this one before. But I actually like to revisit things that we've seen before to see if we can do it now. Okay. we know the likelihood of a particular crime being committed is 0.02 or 2%. If a person really did commit the crime, we're going to represent that with a C. The probability they're found guilty, which we'll represent with a G, is 99%. If they did not commit the crime, they are 98% likely to be found innocent. Okay, so they're going to ask us to find the probability that if a randomly selected adult is found guilty, that they committed the crime. They're going to ask us to find the probability that a randomly selected adult is found guilty and did not commit the crime. And those are going to involve us being careful about what we write out with our probabilities. So she gave you probability formulas at the top of your sheet. We've got all the things we need. Let's see if we can do this. Take a second and see if you can write down what information you were given. And then I'll write down what information we were given. We'll see if we got the same stuff. Okay, things that I think they gave us. The probability that a particular crime is committed would be P of C is 0.02. Did you get that down? Okay. If a person really did commit the crime, that's the same way as saying given that they committed the crime, that they're found guilty is 99%. So you should have probability of G given C is 0.99. And then you might have written your complements differently than me. You might have put the little dashes. I use C's, but if you put dashes, also fine. They said if they did not commit the crime, so that would be C complement. The probability that they're found innocent, which would be guilty complement, is 0.98. So you should have G complement given C complement is 0.98. And that's all they gave us. But we can go get some other information, like the probability of C complement has to be 1 minus the probability of C. So what would that be? Beautiful. We got that one. And something else we also know if I put down given C complement so that it matches the line that we've got up above it, if this one is the probability of G complement, the probability of G, So the things after the given bar are the same. These two things have to be complements of each other as well. So if I'm saying that the probability that they did not, given that they did not commit the crime, that they're found innocent is 98%, then the probability that given they did not commit the crime, that they're found guilty should be the complement of this one. So this should be 2%. You can only do that if the thing after the given bar is the same. Then the complements of those things have to be complements of each other. So those are all things we kind of got for free based on stuff they gave us. Okay, so now let's see what they're asking us. Find the probability that if a randomly selected adult is found guilty, they committed the crime. Okay, so they're saying that given that they're found guilty, so that goes after the given bar, probability that they actually committed the crime. So they're asking you for probability of C given G. Now look up here. One of our givens is the opposite of that, G given C, but they want C given G. That's classic Bayes' theorem. Whenever they're asking you for the opposite of the thing that you have, that's Bayes. So with Bayes, what I always do is she gave you a formula, but I don't even do it by the formula. I look at it and I go, whatever they are asking you for, write the opposite of it. So this would be the probability of G given C, we're turning it around, times the probability of whatever is after the given bar. So probability of C. Okay. Then we draw our big old division line. And then do you remember we write exactly the same thing again right down here? So whatever we just wrote, we're going to write it again. So probability of G given C times the probability of C again. I didn't change anything there. Just wrote exactly the same thing. And then we put a plus sign. Okay. And then the next thing we write is the probability of, and we keep the first thing the same, and then given the complement of the second thing. So G given C complement goes here. And then we always multiply by the probability of that second thing. So probability of C complement. You don't have to memorize that. She did give you Bayes' theorem. So that's written on her formula sheet, but it's going to be written with A's and B's, and the problem she gives you is going to have different letters. So if you can do this without having to look at the formula sheet, it might be less confusing on a test. So again, whatever is here, if it's a Bayes' theorem problem, I immediately write the opposite right there, times the probability of whatever the second thing is. So that's why I'm putting a C there, because after the bar, that's a C. Then you immediately write the exact same thing in the bottom, put a plus sign. Whatever this thing is, you leave the first thing the same, you write the complement of the second thing, and then it's always times the probability of the second thing. That's why it's there. Now here's the cool thing. Probability of G given C, we have that number. Probability of C, we have that number. Obviously, we have both those numbers again here because that's identical, so I have those. Probability of G given C complement, that was one of the things that we found up here. And probability of C complement, we also found that up here. So we have all those numbers now. We're just plugging them in. So G given C is 0.99. Probability of C, 0.02. Writing the exact same numbers again. Probability of G given C complement is 0.02. And probability of C complement 0.98. And if we multiply that all out, we get 0.503 or approximately 50.3%. All right, second one. Find the probability that a randomly selected adult is found guilty and did not commit the crime. So, probability that they're found guilty and is that simple? They did not commit the crime would be C complement. Okay. Now, here's where people sometimes get stuck when we go to look at our formula sheet for this one. G given C complement, the way it's written on our formula sheet says that we would do the probability of the first thing, G, times the probability of C complement given G. And if we do that, we look up here at what we're given and I go probability of G. I don't have probability of G. And so I might think that I have to go do some extra calculations. That's possible. But before you do any extra calculations, I want you to always remember that and means you could flip those around. And so this is the same thing as the probability of C complement and G. You're allowed to write the C complement part before the G. That's okay. In which case your formula would become the probability of the C complement times the probability of G given C complement. And so it's worth taking that extra minute to check because we actually have both of those numbers already. So you don't have to go do any additional calculations. We have probability of C complement. We said C complement is 0.98 and we have G given C complement. We said that one's 0.02. So you don't have anything else we have to do. So if we just take that extra minute to check and see if when we turn it around that it fixes it, there might not be any other calculations that have to happen. So this one is 0.98 times 0.02, which comes out to be 0.0196. Or as a percent, that's approximately 1.96%. So the probability that a randomly selected adult is found guilty and they did not commit the crime is 1.96%. Which is not nothing. I'm glad it's a low number, but you're found guilty and you did not commit the crime. We still have some innocent people up there who are getting in trouble for a thing they didn't do. Okay. Next question. Like, okay, if I was taking this and this was the midterm, like let's pretend this was the actual midterm. This we would have known was probability questions, right? Like, it's not that hard to figure out these are probability questions because she's saying probability, okay? But when we look at the next one, you might not know what kind of problem this is. And that's really important to be able to identify quickly what kind of problem it is. So let's read it. And I'm not going to say what we're going to do first. Let's see if we can figure out what we need. 10% of adults say oatmeal raisin is their favorite cookie. Like, sure. Okay. You randomly select 12 adults and ask them to name their favorite cookie. Find the probability that the number who say oatmeal raisin is their favorite cookie is less than 4. Provide the calculation. Okay. You got a big ass formula sheet with a whole bunch of stuff on it, but it's useless to you if you don't know what kind of problem this is. Okay. How do you know what kind of problem this one is?
Given percentage, so it's probability of each adult and given n as a total, so binomial.
There's a total up there, 12. How do you know that this is not a normal distribution problem? It's not. How do you know it's not a normal distribution problem?
It doesn't say that the distribution is normally distributed.
Doesn't say anything about it being normally distributed. That's great. Okay. Why would you maybe think this one's binomial? It is. How do you know this one's binomial? Because this one doesn't say it's binomial, so how do you know?
There's only 2 outcomes.
That's it. Okay. What can be hard about these ones is that when you read the first line of it, I didn't necessarily know this was binomial yet because it says 10% of adults say oatmeal raisin is their favorite cookie, and then you're asking adults their favorite cookie. Well, they could say oatmeal raisin, they could say Oreos, they could say Girl Scout cookies, they could say peanut butter, like they could give you like a million different things. So from the get-go, I don't know this is binomial yet. Where I know this is binomial is it says find the probability that the number who say oatmeal raisin is their favorite cookie is less than a certain amount. They're only asking about oatmeal raisin. So they're saying it either is oatmeal raisin or it is not oatmeal raisin. Okay. So 10% of adults say oatmeal raisin is their favorite cookie. What percent of adults say oatmeal raisin is not their favorite cookie? 90%. So your P in this problem is 0.10. Your Q in this problem is 0.90 because it's either that oatmeal raisin is their favorite cookie or oatmeal raisin is not their favorite cookie. There's only 2 things here. Even though it feels like there could be more, the way they're asking the question here is just oatmeal raisin or not oatmeal raisin. Okay. Perfect. So this one's binomial. And we've got 2 pieces of information here. We've got that the P is 10%, so 0.10, which means that even though they didn't tell us that, the Q has to be 90% or 0.90. Okay. When they said randomly select 12 adults, they also gave you N. N is 12. Good job. Okay. So now, next part. Find the probability that the number who say oatmeal raisin is their favorite cookie is less than 4. Okay, so probability that X is less than 4. When we do a binomial distribution problem, that means that it could be 3, it could be 2, it could be 1, or it could be 0. So we have to add up the probability that X is equal to 0 plus the probability that X is equal to 1 plus the probability that X is equal to 2 plus the probability that X is equal to 3. Yes.
Right, all the possibilities of X in like a shorter way, we have to always write them all out.
Sometimes it's going to be easier for you to write the complement of the thing, but in this case, the complement of the thing would be that X was greater than or equal to 4. So you would have to write 4, 5, 6, 7, 8, 9, 10, 11, and 12. So you'd have more to write. But in terms of like when you're doing a problem, you're always trying to figure out, is it easier to write out exactly what they asked for or the complement of what they asked for? But other than that, it's not really easier to do anything else.
Always have to write out the probabilities.
You should write out all of them. And here's why. Because what's about to happen is you're going to use the table now. I promised you a table problem. Here's a table problem. This was one of her practice midterm questions. So that's why she gave the table. Okay. What's the N for this problem? 12. Okay, so on the table that she gave you, the binomial distribution table, off to the side, thank goodness 12 is one of them. Otherwise, this table won't work for this problem, but she gave you one that would work. So that's good. Okay. Now, I said we couldn't use this for my problem because our probability, our P was 0.33, which wasn't on there. What's the P for this one? 0.10. So along the top, 0.10 is here. So you have to be careful, not 0.01, but 0.10, 10%. There's only ever P up here. Q is never at the top. So if you're like, I couldn't find the Q, you don't need the Q. It's only asking for the P to use the table. So the P is 0.10. So here's what we got to do. We need the probability that X is equal to 0, 1, 2, and 3. And that's why I wrote all of them out, because we have to add up 4 numbers. Okay, so we're going to go find the probability that X is equal to 0 first. Okay, so on this table, probability that X is equal to 0, I have to zoom out a bit so that you can see the top and also the 12. So it makes the numbers really, really, really tiny, but here's what we're doing. Okay, so we're under the 10. I'm coming down to the 12, okay? Right next to 12, there's 0. This is probability X is equal to 0.282. Then for probability that X is equal to 1, we come over to that 0.10 column. That's 0.377. Probability that X is equal to 2 is 0.230. And probability that X is equal to 3 is 0.085. So what we had to do, we had to know that the N was equal to 12, and we had to know that the P was equal to 10% or 0.10. So then we came down, and then the X values that we're looking for, we said were 0, 1, 2, and 3. So we're taking this number, this number, this number, and this number, and we're going to add up all 4 of those numbers. So I'll write those numbers down here. So probability X is equal to 0 is 0.282. Probability X is equal to 1 is 0.377. Probability that X is equal to 2, 0.230. And probability that X is equal to 3 is 0.085. And so we add up those 4 numbers from her table. And we get 0.974 or 97.4% of the selected adults oh, sorry, 97% chance I shouldn't have written the words out, sorry. 97.4% chance that less than 4 will say oatmeal raisin is their favorite. So of those 12 that we asked, there's a 97.4% chance that less than 4 of them will say oatmeal raisin is their favorite. Question.
So let's say that we decided to take the complement of it instead, like let's say that for whatever reason, maybe we wanted like 10 or more, so we decided to do the complement. In this situation, we would just subtract 1 from what we get, or
1 minus what you got. Yep.
so you would do everything the same and then just simply take like
Mhm. So yeah, if we had asked this question, find the probability that the number who say oatmeal raisin is their favorite is greater than or equal to 4, we would have done the exact same calculation and you would have said 1 minus the 0.974. Yep. Good question. Yes. Yes. So let's just do one of them on there. Do you want me to do the probability that x is equal to 0? Yeah, let's do that one. So let's pretend like you didn't have the table. The table told us that the probability that x is equal to 0 is 0.282. If we didn't actually have the table, here's what we would have done to find the probability x is equal to 0. We would have said 12 choose 0 times the probability of a success we said was 0.10. And we always raise that to the power of that bottom number. Boom. And then times the probability of a failure. So that would be 0.90. And we always raise that to the power of the top number minus the bottom number. Okay. So 12 choose 0 is 12 factorial over 0 factorial times 12 minus 0 with the factorial on the outside. Okay. 0 factorial is always 1. So this is 12 factorial over 1 times 12 factorial. Well, 12 factorial over 12 factorial should just be 1. So this whole thing comes out to just be the number 1. So we have up here 1 times 0.10 raised to the 0th power. That's also 1. And then times 0.90 raised to the 12th power. So we have 1 times 0.90 to the 12th power. So I'm just going to do 0.90 to the 12th power in my calculator. 0.90 to the 12th power comes out to be 0.282. Which is exactly what the table told us, 0.282. So I never taught you guys using the table because I always just do the factorial thing. You don't need the table, but it's probably faster on her test to use the table because she's only going to be able to give you problems. If she gives you the table, her problem's going to have to fit the table. Whereas you guys learned how to just do the factorials for anything, you could solve it for anything. You wouldn't be limited to only certain things that were in the table. The factorial thing always works. Good question. Okay. Second part doesn't require that table, but it does require us to remember a thing. How many adults would we expect to say oatmeal raisin is their favorite cookie? Expect. That's an expected value thing happening. When she says, how many adults would you expect to say oatmeal raisin is their favorite cookie? You're in the land of, on her formula sheet, expected value is the same thing as asking for the mean. So you're going to use n times p to give that.
Why wouldn't we use the formula that like says expected value next? Why wouldn't we use that?
Good question. That expected value formula, is it under the binomial distribution problems? Nah, she just has it sitting there, which is real complicated because people go, ooh, it must be an expected value formula I can use for literally anything. No, this expected value formula is the thing that goes with the table thing we did on Tuesday. So remember there was the table, and what we do is you take each of the rows, you take the x times whatever the probability is, and then we add them up. Well, that's where that sum thing is. And so you do each row times each probability, and then you add, and then each row times the probability, then you add. That's this. If it's not a table, that formula is not going to help you out. So unfortunately, we have to remember that because this problem was a binomial problem, the expected value is going to be the mean formula. Yeah, good question. So our mean is n times p. Okay. Our n for this problem was 12. And our P for this problem was the 10%, so we use 0.10. 10% times 12 is 1.2. So we would expect 1.2 adults to say that oatmeal raisin was their favorite cookie if we asked 12 of them. Okay, we spent a lot of time on uniform distribution problems. A random number generator picks a number from 1 to 9 in a uniform manner. That's how I knew this was a uniform distribution problem. That's important. State the distribution and provide the function f of x. Well, the good news is she put that on your formula sheet. So uniform distribution f of x formula is 1 over b minus a or 0 otherwise when we're talking about from a to b. The uniform distribution part of it, you would say that x is uniform. And we always put the a first and the b second. Our a is 1 and our b is 9. So your f of x is equal to 1 over b minus a which would be 1/8 for x is greater than or equal to 1 but less than or equal to 9. And it's 0 otherwise. That's straight from the formula sheet, so you don't have to have that memorized. But what you do have to remember is what we just got. When we're doing uniform distribution problems, what's the shape that the graph always is? It's a rectangle. So when we just did that 1/8 right there, what is the 1/8 on the rectangle? It's the height. This is always the height of the rectangle. This 1/8 right here is the height of the rectangle. Cool. So the next part's, she had formulas and stuff, but I always do this just by drawing the rectangles. So it says, find the probability given x is greater than 3 that x is greater than 5. So if I draw you a rectangle then, and that rectangle goes from 1 to 9. Oops, not 9. 1 needs to go there. Okay. The height on that rectangle is 1/8. Okay. And what you're going to do is you're going to have a numerator and a denominator here for your probability that x is greater than 5, given x is greater than 3. Okay. Probability that x is greater than 3 came after the given bar, so that's the denominator part. So we're going to do the area of the rectangle where x is greater than 3. X is greater than 3. So if that's 1 and that's 9, 3 is maybe like here. So I want the area of this rectangle in the denominator. We know the height is 1/8. I now need the length of the base. What's the length of the base from 3 to 9? So that's my base. Times my height is 1/8. That's going in the denominator because that part is the thing that came after the given bar. In the numerator, I want the probability that x is greater than 5. So greater than 5, I'm going to say 5's like maybe right here. I want the area of that rectangle in the top. The height's going to be 1/8 again because the height isn't changing. What's the base if we're just going from 5 to 9? 4? 5 to 9 is 9 minus 5, 4. Is that okay? Cool. Now, 1/8 is in the top and 1/8 is in the bottom. So are you cool with me just like canceling those out? So your answer is going to be 4/6, which we could simplify to 2/3. There's your probability. Yes.
Is it possible for us to just use the like area formula to just find, like if we just multiplied like 4 times 1/8, because we're just finding the area of the purple square?
Yep. That's the area there. 4 times 1/8. You could do 4/8, which would give you 1/2. And then this would give you 3/4. If you take 1/2 and you divide it by 3/4, you're still going to get 2/3. So you can calculate the area. That would give you the area, base times height. And that would give you the area, base times height. But since they were the same height, I was making the calculation simpler because if the height's the same, you can cancel it from the top and the bottom. So, but yes, you can calculate the area and then simplify last. Also going to give you the same number. Yep. Are you scared it doesn't? The area on the top would be 4/8, right?
No, I was just it's just like a different way of doing it.
Yeah. The area on the top would be 4/8. Area in the bottom would be 6/8. And so if we want to divide a fraction by a fraction, you keep the top fraction. You change this division bar into a multiplication dot, and then we flip over that bottom fraction. So it would be 8/6. And then those 8s actually cancel. So we get 4/6, which simplifies to 2/3. So we get the same answer. Yeah, you can do the area divided by the area.
If we're to do it like that, can we leave it as 4/6 as our answer and choose so we count this right?
No idea. I would hope so. I would hope so, but I don't know. 90th percentile. Good news is, under her uniform distribution, she gives you a percentile formula, so you don't have to memorize this. You're going to put 90 where the K is. So 90/100 times, and then the bigger number minus the smaller number. So you're going to do 9 minus 1 plus 1. So our 90th percentile is 90/100. The B was 9, the A was 1, and we're supposed to add it to the A. So 90/100 is the same thing as 9/10 times 9 minus 1 is 8 plus 1. This is 72/10 plus 1. 72 divided by 10 is 7.2 plus 1 is 8.2. It says, draw a diagram to support your work. No problem. Our original rectangle went from 1 to 9. Okay. And the 90th percentile should mean that 90% of that rectangle is filled in. So 90th percentile, if you had to guess where that is, I'd say it's like maybe like right here. Does that feel like 90%? Maybe not even. Maybe it's even further over. Maybe it's more like here. So 90th percentile should mean that you've almost got the entire rectangle filled in, right? And then there's just a little bit left. Would it make sense that the number where this part ends is at 8.2 based on the number that we got? Yeah. So along the bottom, if you were shading everything in all the way up to that number 8.2, that would be where I would guess that you would hit 90th percentile. So that makes sense. And her last page. The amount of rainfall in January in Davis is normally distributed. Big ol' hint. With a mean of 4.9 inches. And a standard deviation of 0.3 inches. Okay. What is the probability that for a randomly selected year, it rained more than 5.5 inches? And she wrote Z is equal to 2, which you might be like, what? What she's saying is if you were to do this calculation yourself, for a randomly selected 1 year, you'd be doing your Z formula, x minus the mu divided by the standard deviation. The x value that you'd use is the 5.5. Minus the mean is 4.9 divided by 0.3. And what she's saying is that if you didn't have a calculator, what's going to pop out of that is Z is equal to 2. So when she put Z is equal to 2, she did the calculation for you, but she still wanted to see you do it on your paper. So 5.5 minus 4.9. And if we divide that by 0.3, it comes out to be 2. So she gave you the correct answer, but she still wanted you to just show the work for it. She does that a lot.
Is that what she?
Yep, that's why she wrote must show all work to receive credit. So she told you Z is equal to 2 because some quarters she didn't let people use a calculator. So she just wanted them to write that part out. And she was like, she knew people were going to get stuck right there and go, I don't know what that answer is. And she's like, don't worry, it's Z is equal to 2. Now, that's just the Z value, though. The question says, what's the probability that it rained more than 5.5 inches? If I go take that Z value, I'm going to have the wrong answer. I got to do 1 minus whatever the P value is that I get. So I'm going to go find the P value, and then I'm going to do 1 minus that P value for my actual answer. So Z is equal to 2. That P value is 0.9772. And so if it had said, find the probability that it rained less than 5.5 inches, that would be the right number, but it says more than, so we got to do 1 minus 9.9772. And that comes out to be 0.0228 or 2.28%. I'm going to not write the full sentences just so I can finish. So it said, what's the probability that for a randomly selected year? So we just used our normal Z formula for that one. The next one says, what is the probability that the mean annual precipitation during 16 randomly picked years will be less than 5 inches? Now we're using central limit theorem. Normally we need it to be 30 or more, but how come we're okay on this one? Normally distributed, so we're still good. So we're going to do our Z is equal to the X minus our, the X bar, hold on. Yep. Why am I blinking on what I'm writing? Oh, our X bar. Oh, I'm blanking because I'm writing the wrong thing. That's why. I wanted to write the mean for the X bar. There we go. And then we're going to write our standard deviation for the X bar, which means you're doing your 5 minus our mean 4.9 over the standard deviation 0.3 divided by the square root of our n. And our n this time was 16. Okay. So in the top, we got 0.1. In the bottom, we got 0.3 divided by 4. $1.33 is the z value. And that matches with the z value she gave us off to the side. So she said 1.33. I feel good that we also got 1.33. All right. This time, it said less than 5 inches. So we just need to go find the p. We don't have to do 1 minus the p. So 1.33. 0.9082. Or 90.82%. And then the last one is a little trickier. Find the value of the quartile Q1 for the total annual precipitation during 10 randomly picked years. So we've got that word total in there again. So that means we're talking about the sum situation. So the sum, when we did this before, if we wanted the sum then what we did is you multiply the n times the mean for just one of the x's. So our n times the mean. 10 randomly picked years, 10 is our n, and the mean was 4.9 is what we wrote for just one of them. So 10 times 4.9 is going to give you 49. Standard deviation for the sum. The formula says we want the square root of the n times the standard deviation for just one. So we want the square root of 10 times our standard deviation for one was just 0.3. That one doesn't come out quite so nice. Square root of 10 times 0.3 is about 0.95 if we round it. What we need now is to use this idea of the first quartile. That's a percent. First quartile is 25%. So we need, whoops, sorry. We only has one E. We need the Z value for 0.25. So remember on a Z table, the middle part is the percentage part and the outside part's the Z's. They're giving us the percent. They're saying the quartile is 25% and that we need to go find the Z value that corresponds to that. That's going to be on the negative Z table. And 0.25 is right here. So that's going to be 0.675. 0.675. With a negative, sorry, negative 0.675 because we were on the negative Z table.
Why can't you do 0.7?
So when it's right in between them, she's got on the directions on the bottom of her table, if it's between the two numbers, what we do is we go between the two values. And so it was between these two values. So we're going to do 0.675 because it's in between the 0.7 and the 0.8.
So I did ask her about that during lecture. She was doing something different. She had
Oh.
told us to pick the value closest.
Oh, okay.
So I did ask her about that and she said she did want us to pick the closest value.
Okay.
Unless it was like a specific kind of problem.
Got it. So she wanted it to be 0.67 for this one?
I think so. Yeah, she wanted us to pick the closest value.
0. We'll say 0.67 then. So she's like, ignore the instructions on the bottom of the page. Okay, we'll do. We can do that. All right. And now what we're going to do is you're going to take on her formula sheet. She has X is equal to the mean plus the Z times the standard deviation. So our X is equal to the mean of the sum for this one, plus the Z times the standard deviation for the sum for this one. So we're going to put in the mean value of 49 plus the Z value negative 0.67. And then we're going to multiply that by the standard deviation 0.95. And if you combine those, 49 plus 0.67 negative times 0.95 comes out to be 48.36. We need a unit on this one. It's saying the total annual precipitation. They were giving us precipitation in inches. So this will be 48.36 inches is our first quartile. All right. Sorry, I went a few minutes over, guys. Good luck on Friday.
Since I have a question, since it says the amount of rainfall in